in the previous class, we have talked about unbalanced and non-sinusoidal three-phase system. We were discussing how to represent this kind of system with the help of the voltage and current expressions. As you can see here, that these voltages and currents are unbalanced with respect to their magnitudes as well as their phase angles. They are different. Alpha AN, alpha BN and alpha CN. Similarly, current we have a beta AN, beta BN, beta CN, and amplitudes are IAN, IBN, ICN. For that, we have found the instantaneous power by multiplying voltage and current for each phase. This we have solved in the previous class, that is BAT into IAT plus BBT into IBT and then plus BCT into ICT. We have resolved into similar and dissimilar frequency component, and in the similar we have resolved into active and reactive components and then the rest of the powers. From that, we also have found the total real power and the reactive power, capital P and capital Q, in terms of the phase real and reactive powers. Today we will continue the same discussion to find out the apparent powers or different kinds of apparent powers for this system and then the power factor based on this. Now, as you know, the apparent power is the product of the RMS value of voltage and current. Now, since here the voltage and currents are unbalanced as well as they contain harmonic, so we have to find the phase wise apparent powers. Okay, that actually means that we have to find out SA, SB and SC. So this is SA, this is SB, this is SC. How do we find out these values? By multiplying RMS value of A phase voltage and currents. So BA into IA. This is also equal to PA square plus QA square plus DA square, because the system is unbalanced and it concerns the harmonics. If you compare the each phase with the single phase system that we have described, then we can correlate the relationship of P, Q and D to BA into IA. Similarly, for phase B, BB into IB equals PB square plus QB square plus DB square. And for phase C, it is BC into IC, that is PC square plus QC square plus DC square. You may have doubt that for this case, can we find out SA bar equals to BA into IA conjugate? You cannot use this expression because the BA consists of many phases. BA consists of fundamental, second harmonic, third harmonic and so on. So phasor of voltage A exists at different frequencies. So you cannot use a single expression like this, but you can use the individual expression for each harmonic frequency. For example, we can write like that: this is SA1 complex, then this is SA2 complex and so on. That can be done. Okay, and then we can add in different manner. For example, we can use arithmetic sum. We can take mod of each and take the overall mod, or we can first the sum on the vector basis or phasor basis and then we take mod. Okay, so there are different possibilities, but definitely this SA bar, which we have found by summing the individual frequency complex powers for phase A will not be equal to BA into IA. Okay, so this analogy will not be true. You cannot say that this is equal to BRMS into IRMS. Therefore, we use this method to solve it for different value of apparent powers for phase A, for phase B, and for phase C. Now, based on this, we can also find out the SA, SB, and SE, which are known as arithmetic, vector, and effective apparent power. SB will be square root of P square plus Q square plus D square. Now, what is P? P is the sum of real power of each phase. That you can see here. P is PA plus PB plus PC. Okay. So this P is sum of PA, PB, and PC. Similarly, Q is the sum of QA plus QB plus QC. And then D is sum of DA plus DB plus DC. You may ask, what is DA, what is DB, what is DC? The DA, DB, and DC can be found from these expressions, because I know PA and QA. PA, QA you can find out from the phase A. From phase A, we know what is BAIA, and we know what is PA, we know what is QA, then we can find out DA. So actually, DA will be nothing but SA square minus PA square minus QA square. And SA and PA and QA are known to us. So we can find out DA and DB and DC. PB square, I think I have given down, but just let me complete it. P square, and then DC will be SC square minus PC square minus QC square and square root. So once we know the distortion powers DA, DB, DC, then we can find out capital D and capital Q and capital P accordingly. Now we will find out the different power factors based on this. So power factor arithmetic will be P by SA, power factor vector will be P by SB, and power factor effective will be P by SE. Correct? Now SA will be SA plus SB plus SC. There is a difference between SB and SA. There are three definitions, as I said. One is the, let us say, vector, and then arithmetic, and then effective. So vector is fine, P square plus Q square plus D square square root, and arithmetic will be the algebraic sum of A, that is SA, SB, and SC. This will be the value of SA. Okay, but SB is P square plus Q square plus D square square root, and they are not equal, because the Q is sum of QA plus QB plus QC, that may have considered the sign of each reactive power. So obviously SB will be less or equal to SA. So this property still holds true, that if you find out these values, you will find out that SE is greater than or equal to SA is greater than or equal to SB. And accordingly, the power factor E will be less than power factor A, will be less than power factor based on the vector apparent power. PFB. Okay, we will see in the example how they are true for unbalanced three-phase system. All right, So you know how to compute the arithmetic, the vector, and the effective apparent power. And based on that, we compute the power factors. And finally, we choose the power factor which is the least in value, and obviously that power factor is the effective power factor for the design of the distribution network. Now, let us focus on the SE. For this unbalance with distortion, how will you compute the value of SE? So we have defined the SE as 3 times of BE into IE. And we also have defined the value of BE and IE based on the same losses and same output. We have proved earlier that the value of IE is nothing but IA squared plus IB squared plus IC squared plus IN squared by 3 and square root of that. And the value of BE was 1 by 18th, 3 into BA squared plus BB squared plus BC squared plus BAB squared plus BBC squared plus BCA squared, and the whole thing 1 by 2. These are the definitions of effective voltage and currents based on the previous study, or based on the same losses and same power output for 3-phase unbalanced voltage with fundamental. See, we have defined these terms for the 3-phase system or 3-phase unbalanced system with fundamental unbalance. However, we are extending this idea to 3-phase unbalanced system with harmonics. Okay? So let us now find out what is the effective current. The effective current, as we have defined, is IA square plus IB square plus IC square plus IN square by 3 square root of the whole. Now we can express this IA, IB, IC in terms of the fundamental and harmonics. Okay, so fundamental is IA1. So IA square, that is RMS value of A phase current square, can be written as IA1 square here, IA2 square, IA3 square till IAH square. Similarly, IB can be written as IB1 square, IB2 square till IBH square. And then IC can be written as IC1 square plus IC2 square till ICH square, and IN can be written as IN1 square plus IN2 square till INH square. Divided by 3 from this and the square root of this. Okay. Now if we simplify this, just collect the fundamental terms together. So these are the fundamental. This is the second harmonic for each phase current, and this is the nth or hth harmonic for each phase current. Now this fundamental can be called as IE1 square. This term can be called as IE1 square, and this whole thing can be called as IEH square because it consists of harmonic component from second harmonic to the hth harmonic. So this whole term can be referred as IH square. So this is here actually IEH square. So now IE is nothing but IE1 squared plus IEH square. Okay. So what is the difference between the previous and this expression? In the previous case, there were no harmonics. So in that case, IE square was just IE1 square. But now there is an additional term, that is IEH square. That takes care of the harmonics of the equivalent current. All right. Similarly, we can find out the phase, effective phase voltage, or BE. Just replace the BA, BB, BC in terms of its fundamental and the harmonic component. So earlier we have defined, this is the expression for BE, 1 by 18, 3 times of BA square plus BB square plus BC square, and then plus BAB square plus BBC square plus BCA square and square root. Now replace them by their fundamental and harmonic component, then this becomes 3 into BA1 square plus B1, 3 into BA1 square plus BB1 square plus BC1 square. This is 1 here, BC1 square. And plus BAB1 square plus BBC1 square plus BCA1 square. So this is the fundamental term from here to here. The remaining are harmonics. And therefore, we can write this in terms of the BE1 and BEH. So BE is nothing but BE1 square plus BEH square. Again, previously when we have studied the three-phase unbalanced circuit without harmonics, this term will not be there. So in that case, we will get only BE square equal to, in fact, BE1 square. But now, because of harmonics, we will get BE square equals to BE1 square plus BEH square. Similar to the current, where we got IE square equal to IE1 square plus IEH square. Fine. Now let us find out the effective apparent power, because we already have computed the value of B and IE. So substitute this value of B and IE and see what do we get. So this is 3 here into B into IE. So 3 is, this is BE, BE1 square plus BEH square, and this is the IE. Okay, that is IE1 square plus IEH square, square root of that. We square both the sides to simplify it. So this becomes as E square. 3 into 3 becomes 9. So first term is 9 into BE1 square, IE1 square. Then H into H, 9 BEH square, IEH square. Then BE1 into IEH. So this is 9 BE1 square, IEH square. And then last one is 9 BEH square, IE1 square. Here we will use the concept of total harmonic distortion definition. Okay, this can also be written as SE1 square. This is SE1 square. This is SEH square. This is DEI, distortion effective power, because of distortion in current. The harmonic is present in the current, therefore distortion is because of current. And this term is DEB square, distortion because of the voltage. Okay, so this is DEB square, and this term is denoted as SE1 as such, and the whole thing is called as SEN square. So this is SEN square for this. Okay, now we can also simplify it using the definition of total harmonic distortion. The TSD EI equals to IEH by IE1. If you remember earlier, we have defined TSD. Let us say I equals to IH by I1. Now E is additional subscript. So this is E, this is E, this is E. That's all. Similarly, TSD in voltage is expressed as BEH by BE1. So use these definitions to simplify the expression for the apparent power. So replace this EH, IEH, BEH using these expressions. So you will get this term comes here, okay, and IEH becomes basically B1 square, I1 square. This becomes, this is here, and THD EB square comes because of voltage, so this is here. Now we can take common SE1 square. We will get the expression. Okay, now take common SE1 square from all the terms. We will get 1 plus THD EB square, THD EI square. This is THD EB and THD EI square, product of this. And from this we can correlate the SE and SE1. SE equals to SE1, the whole thing is square root. Now once we know SE, then we can find out the power factor based on this definition. PF is given as PYSE. Therefore PYSE is P1 plus PH, because P is given by P1 plus PH. Okay, so this is P1 plus PH, and this is SE in terms of SE1 and THD components. Again we can take common P1, so this becomes 1 plus PH by P1 into P1 by SE1, because SE1 will come from the denominator. Okay, so this becomes P1 by SE1, and divide by the whole term in terms of THD, and then square root of that. Okay, so once we know this, then we can simplify a little more, saying that THD in current is far greater than THD in the voltage, and therefore this can be ignored, this can be also ignored. Okay, so this will go away. So finally we can say the PFE approximately equal to PFE1 by 1 plus THD EI square. What is PFE1? PFE1 is nothing but power factor for fundamental voltage and current, or effective fundamental voltage and current components, PFE1, and this is PFE. Okay, so this expression is for three-phase unbalanced system with harmonics, where you find out the power factor based on the effective apparent power. So now you know the vector, arithmetic, effective apparent power, how to compute. We can take one example to prove or to find out these values. In the previous class we have defined the fundamental, the unbalanced power as U simply. So SU was SE square minus S plus square. This is called fundamental apparent power. So same expression is for fundamental, that is SU1 equals to SE1 square minus S1 plus square. What is SE1? P1 square or P1 plus square plus Q1 plus square. What is P1 plus? P1 plus is 3 into BA1 plus IA1 plus cos phi 1 plus. Q1 plus is 3 BA1 plus IA1 plus and sin phi 1 plus. And this is the PF1 for positive sequence fundamental powers, that is P1 plus by S1 plus. Okay, so this makes the complete description of three-phase unbalanced system with harmonics and unbalance. We have found different power expressions and various apparent powers, and based on these powers we have found the power factors. Now let us take one example and feel it, that how this is there in the three-phase unbalanced system. So we'll start with this example 3.5, where we have considered a three-phase system, okay, with the voltage as 220 volt at point A dash, B dash and C dash. So actually we have considered a distribution system with 220 volt, and it is supplying first a balanced three-phase load, star connected load. The value of three-phase balanced load, resistive load is 1.3 ohm, and the output power is 100 kilowatt. The losses in the feeder are 5%. Okay, and we did not consider the reactance of the feeder in this problem. So find out first the load voltages at the terminal voltages or the load voltages, phase currents and feeder resistance. Feeder resistance is not given to us. We have to find based on the losses. And the next part, we make this system unbalanced by placing a resistance between point A and point B. With this configuration, we have to find the active reactive components and the losses and compare the losses with the previous system. In C part, we have to find the equivalent circuit for B part. That is, for this unbalanced circuit, what is the equivalent balanced circuit in terms of the losses and the output power. Alright, so let us go ahead. This is the system description. As you can see, three-phase system. First, in the beginning, we are supplying this three-phase load RA, RB, RC with feeder resistance small r, and this voltage is 220 for each phase with a phase displacement of 0, -120 and +120. So let us first find out what is the power output. So power output is nothing but 100 kilowatt. We want to deliver 100 kilowatt power. So for that, the voltage at the load is B. We are considering this voltage as P here. This RMS value is B. So the total output power will be 3B square by R. So 3 into B square by R. This gives the value of voltage at the load point here. Okay. So if you solve this, then we will get this voltage as 209.76 volt. So BA is this much, BB is this much, BC is this much. The angle will be same as the A dash, B dash, C dash because it is purely resistive load. So there will be no shift in the angle of the voltage. The only change in the magnitude because of the losses here. So, or because of the drop across the feeder. Okay. So this is B dash here and this is B. So this B dash is 220 volt and this is actually 209.76 volt. The next step is to find out the feeder resistance. You can also find out the voltage drop. Delta B will be nothing but B dash minus B. This is the voltage drop. So it's about 10.24 volt, around 10 volts voltage drop. That is quite acceptable. Now let us find out the value of resistance for which we get 5% losses. So since losses is 5%, so 0.05 into 100 into 1000 watts for the value of a small r, 3 into I square into R. Because it is a balanced circuit, it will be 3 into I square into R. So this gives the value of R as 0.06 ohms. Okay. So this is the value of feeder resistance that has to be considered for this system. Now let us find out the apparent power, arithmetic apparent power, vector apparent power and the effective apparent power. Now since system is balanced, all three powers will be same. because for a three-phase balance system without harmonics, okay, all three powers will be same, and hence all three power factors will be same. You can find it out. For example, the arithmetic is sum of SA plus SB plus SC. Since they are balanced, so they are 3 into B into IA, it becomes 100 kilowatt. So arithmetic apparent power is 100 kilovolt amps. And for vector, it is P square plus Q square. There is no D because there are no harmonics. If you solve this, you will get this same thing again, 3 into BA into IA, 100 kVA. And then you find out the effective apparent power. Since it is balanced, so it is 3 into B E into IE, B is same as B, I is same as IA, BE is same as B, and IE is same as I, and therefore it is 3 into BA into IA. This is also 100 kVA. So since the three powers are same, and therefore the power factor based on these apparent powers will be also same, that is unity, because there is no reactive power in the circuit. Okay, so till that is not a problem. It is very simplified. Even without solving, we can tell that for this system the power factor will be unity at the load point, and the three apparent powers and three power factors based on them will be same. Now let us consider the second part of this question, where we have discussed that, where we have asked that a resistance is connected between A and B to supply the same output power. So R we already know, that is 0.0066. So this R is 0.066 ohm, and this R is, we do not know it, but we have to find this R in such a way that P0 is same as the previous one, that is 100 kilowatt. So we have to use two equations here. Number one is output power. So output power is 100 into 1000, that is IA square into R, because there is only one current flowing here. So from that we will get IA. Okay, but from this circuit we can also get IA, that is BAB dash by R plus 2R. This is BAB dash by 2R in the loop plus R. So this IA is also equal to BAB dash by 2R plus R. Substitute the value of BAB dash, since it is a balanced three phase, the input, so it becomes root 3 line to line voltage into 220 into 30 angle. This is 2 into R, this is R. Now if you solve these equations, that is IA equal to this much and also equal to this much, if you solve these equations you will get quadratic in R. Now from this the values of R are found, and there are two values, one is 1.17, another value is 0.015. So we will choose the highest value of resistance so that there is a less current. Okay. So the feasible solution will be R equals to 1.17. This is the value of R. This value is not chosen because it will give the high current in the phases. Okay, so for this R, we can find out the current, because I square R will be equal to 100 kilowatt, and therefore the I will be 100,000 by 1.17, that is 292.35 amps. So this is the current that will flow in phase A and phase B, because it is three-phase unbalanced system. Now IA is therefore 292.35 angle 30, because IA will be BAB by R, and BAB will be shift of 30 degree. So this is the voltage which is coming out as I angle of 30 degree. Okay, so this is IA, and IB is minus IA, and IC is 0. This is same example as we have solved earlier. Now with this BA, IB and IC, we can solve for BA and BB and BC. BA is BA dash minus the drop across the feeder here, and BB will be equal to BB dash minus drop across the B phase feeder. So this comes out to be 203.55 angle of minus 117.29, and this is 203.55 angle of minus 2.7. BC is same as BC dash because there is no current. The current is 0. Therefore, BC is same as BC dash. So once we know BA, BB, BC, we know IA, IB, IC, we can find out SA, SB, SC. Okay, this is SA, this is SB, this is SC. SA is BA into IA conjugate. If you solve this, you will get the value as PA plus JQA. So QA is negative actually. And from that, the SA is the mod of this, that is, the value is 59,522.46 volt amperes. Similarly, SB can be found, and the value of SB is same. The only difference is here it is plus J, it is minus J. Okay, and the value of SC is 0. So once we know SA, SB, SC, now we can find out the different apparent powers. So what is SA? SA is sum of SA plus SB plus SC, which is 119 kVA. Okay, you can also write in form of kVA, 119.09 kVA. And SB is the sum of the complex power and its mod, that is 100.17 kVA. And SE is 3 into B into IE. Substitute the value of B and IE from this expression, you will get this is 149.82 kVA. So we have now 3 apparent powers, and all these 3 have a different values. Based on that, the power factors are 0.84 arithmetic power factor, 1.0 as vector power factor, and 0.667 as effective power factor. So when you design the network, the feeder, you will consider this power factor to decide the rating of the current for the conductor, because this will give the highest value of current and we will safeguard the operation of the transmission or distribution network. This will give the highest power factor, therefore lowest current. So it will not have enough margin of safety when there is an unbalance or when there is a fault. Okay, this is in between. So we shall prefer the effective power factor for the design of the distribution network or transmission network. And you can find out the losses actually. Okay, the losses will be IA square R, IB square R, and IC square. These losses are actually 11.26 kilowatt. So you see the losses have doubled. This point we also have proved in case of the previous example. Now the C part you can solve yourself. I will just give in 2-3 minutes. In the C part, you have to find the equivalent 3-phase circuit for the part B. that is for the output power of 100 kilowatt and losses of 11.26 kilowatt, what is the equivalent three-phase circuit and what is its power factor. Okay, so let us say that there is a equivalent circuit or there is a balanced circuit for the B part of the question. Then the losses are 11.2 kilowatt, so 3 I square R will be 11,260, okay, and this will give the value of I. So I will be 238.47. What will be the resistance of load? The resistance of load is computed using the output power P0. So P0 is 100 kilowatt and from this R can be found. So R comes out to be 0.59 ohms. The total input power must be the losses plus output power. That is 111.26 kilowatt. So this input power must be equal to 3 into B into I cos phi. Cos phi is the power factor in the phase of the balance circuit. So this gives the cos phi as 44.92 degree. And cos phi tells us that there is a presence of reactance. Therefore, tan phi is tan of 44, that is 0.99, and this tan must be equal to x by r plus r in the phase. So this gives the value of r as 0.65. So you see the impedance is now 0.59 plus j 0.65. You can see it here. This is the equivalent circuit. For P0 equals to 100 kilowatt and P loss equal to 11.2 kilowatt. So you can see here the equivalent balance circuit is in terms of R and X. And if you find out the value of this power factor, okay, that is actually the cosine of 44.96 and that is 0.67. All right, and you can compute the voltage and currents for the phase A and phase B, phase C, and you can find out the angle between BA and IA. So this is minus 44, this is minus 3.03. Okay, so minus 44.94 minus 3.03. So cosine of this whole thing will be nothing but 0.67. And this power factor is what we have got earlier. If you see the previous expression as E here, okay, the PFE was 0.667. So this is matching with this equivalent circuit that we have found based on the same output power and same losses. Okay, so we have proved the concept of that power factor must be the least power factor, and that belongs to basically the effective power factor. So for the design of the three-phase unbalanced system, we normally consider the effective power factor, which represents actually the power factor of three-phase equivalent balance circuit. This we have just now proved it. And there are examples in the book. You are supposed to go through them, and answers are given for some of the numerical problems. So solve them. So there are almost 20 problems, I hope. All right. And similar type of questions will be asked in the examination. So with this, the unit 3rd is completed, and in the next class we will start the next unit, that is called the load compensation techniques.